Welcome back. Hey everybody, good to see you. So we planned to do this distributed task queue, I think back in February. A couple of things had happened since. So it's time to resume. It was planned to be a two episodes episode. In the first one, we talked mostly about Kafka and Rabbit, with my preferred way of diving straight into consistency, linearizability, guaranteed delivery, and stuff. That turned out to be a good episode by itself. I think it was almost 2 hours. Or was it like 1.5? Anyways, it was long. Today, we may well be shorter, which I think would be awesome. So I'm actually hoping for this to be under an hour, which means it is even more valuable. If you have questions, just don't hesitate. It's time to start housekeeping on the meetup, on the event. I'll try to keep it super quick. I think last time I checked, honestly, 30 minutes ago, we had 999 subscribers, so chances are, while we're talking, we're going to cross 1,000. Thank you and welcome. It's still my hobby. I'm still having my beefs in terms of moral compass on this dichotomy between becoming better engineers and architects and interview prep. So I'm fully aware a lot of people are finding this because it's good content for interview prep. I don't think I have any way to not make it interview prep, but my goal, my spirit, is to gather smart people so that we can talk about stuff. I'm not going to focus on interview prep, but I'm fully aware it's an interesting application of these events. My dream actually is to have what I call the Architect's Corner. So on the unofficial events, we can actually talk semi-confidentially about real-life problems and share ideas. It's partially true these days. On the off-the-record events, we have approximately 2 off-the-record events per one recorded event. On the off-the-record events, we often get to talk about these kind of things, as well as some flavor of the industry and stuff. So my dream is partially complete. My dream is partially accomplished, but there's a long way to go. I just wanted to put this out in the air for everybody to get the message. This content should be helpful for interview prep, but that's not my goal, and I hope it will never be. All right. So the way the problem is usually postulated is that we need to schedule and run tons of tasks per day. It's really hard to put a number to what tons of tasks means. So my instinct is pretty simple. It's kind of too easy if it's in the order of 1 per second or less. So let's talk about at least 1,000 per second. 1,000 per second is approximately 1 million per day. I think there's another 1 or maybe 2 orders of magnitude reserve. So any good solution that can handle millions of tasks per day could do, let's say, 100 mil easily. If you want to go to billions of tasks per day, chances are you're not really designing a task queue. You're not really working on scheduling tasks. You're working on scheduling trivial pieces of work, which is a lot like actor models, except it's not multi-core within the CPU. It's multi-node, multi-server within a data center. So chances are, if it's this scale, you want to do something else, not the standard task queue problem. You would not have filtering, you would not have priorities, you would not have dependencies as clearly as you do for, let's say, in the order of million per day, in the order of 10 per second. When I think of task queue, we will get to the dichotomy between high performance versus more control. We'll get to this shortly, but in the order that is loosely resembling from more offline, more batch, to more real-time, I would say something super offline would be an application. Let's say you have a service, and what it does is video processing. Maybe you want to blur the background for all the participants, maybe work on the sound quality a bit. You can build a company like that, you can make money, and the core business would be eventually users submitting their videos, which are multi-gigabyte files, and then sometime later, they receive the result. So that's an example of a task queue. You would have a bunch of servers, could be tens, could be hundreds, could be thousands, but approximately less than once per second, you will be having a new job scheduled. I would say, well, maybe a couple times per second, but not too frequently. That's literally the most low throughput example I can think of. That's where we all understand that a single machine doing this arrangement, doing this task assignment, could do the job in terms of performance. We'll get to durability, high availability, all the guarantees, but fundamentally at this scale, there's not too much CPU work involved. Then if you go further down with respect to throughput, I would say after this video-based processing, you'll get to OLAP, online analytical processing, so data warehouse reports generation. Let's say you have some report to be generated. If it's a legal report, if it's a fiscal report, it could be something like daily, every midnight or so. But maybe you have more actions that happen every hour, every 15 minutes, or maybe per some action. Some bank is doing something big. If it's a gambling service, some poker tournament table is closed. You need some report. This technically fits for the task scheduling job. The canonical example of a task queue would be one of the big parts of the web crawler problem. So in my head, again, we're in the interviewer head. If I'm talking to the candidate about web crawling, I would say at least half of the conversation should be about how do you schedule the crawl tasks. You need to ultimately crawl the pages, you need to parse them, but the fundamental challenge would be when does which node crawl which page and at which frequency, how do you recrawl them? And then moving down this list, it's similar to web crawler, but it's far more frequent. Let's say you build in PagerDuty, or you have a service that needs to monitor health of other services, which means you will have probably millions of other services under your supervision, under your monitoring. You want to ping each of them every 5 seconds, every 30 seconds. So that's a huge, large-scale task scheduling mechanism that would be the core of your business. So that's a more canonical example of distributed task queue. If we go all the way to, let's say, Twitter, when you have celebrities with millions and millions of followers, and some of them could be online right now, and if a celebrity tweets, probably you would like people who are online to get this content right away. If the user is offline, what you would do in practice is send them an Android or iPhone push notification, which does not require a queue. You just send a message to the service. But when it comes to people who are online, so you have your own front-end cluster, you have tons of WebSockets or GCP sockets open, in order to distribute this task, in order to dispatch this task everywhere, chances are you would need to have something like a task queue. So I think the latter example with Twitter is probably out of scope of a standard task queue, but somewhere up until approximately that point, so millions per day to maybe 100 mil per day, that's what we are going to cover today. I like this problem, distributed task queue, largely because it has this unique property that when I speak with people about it, the way you postulate it, the way you formulate the problem statement, in a way it tells more about how you reason about system design than the actual solution. So it's one of those problems where it's a lot harder to agree upon what exactly I was solving for than to solve the problem. So in fact, in this episode, talking about how to approach the problem would be even more in-depth and probably longer than talking about how to solve it. So in my head, I found 3 layers of how can I postulate this problem, and let's go through all of them. Three tiers, I would say. So tier 1, which I call the basic tier, is how would the trivial problem statement look like? What you want is you're going to schedule tasks, get their status notifications or reports. You want to have a retry policy. A lot of people talk about recurring jobs, so like a distributed cron, something has to be run every midnight or so. You want to have some monitoring. You want to have some state of the fleet so that you know if some machines are down, or you know if you have too many tasks and your cluster that runs the jobs is too loaded. You need to add machines or drop some tasks. And at this basic level, at this basic tier, you want some sort of durability and availability, but you don't care much. If you lose a task every once in a blue moon, you don't care. If it's double processed, it doesn't really matter. You just do your best effort. You assume that if you have a database, the database is reliable enough unless something quite rare happens. You assume you use some lock-in, and lock-in takes care of double processing unless something bad happens. And in practice, I will use this phrase a couple times in this episode. In practice, best effort is good enough for the task queue. So we're going to get to advanced and expert modes where you can actually do a lot better. But I need to stress this enough. In practice, you don't need to go this deeply. It's more about how you reason about the problem, and it's more me picking into the details just because I think it's a lot more fun and interesting. So the web crawler download queue would be a good example here. If you crawl the page twice, if you crawl every 10th page twice, nothing would break. In practice, it's really hard to build a system that would crawl every 10th page twice. If you crawl every 10,000th page twice, the users would not notice, realistically. If you forget to crawl some page, also no big deal. So you need some really basic best effort crawl queue, which is kind of trivial, to be honest. And when I try to reason about how to distinguish between these tiers, basic, advanced, expert, the best analogy I found is look at the mindset of the user who's postulating the problem. So the basic problem statement mindset would be, I need to have some tasks scheduled. That's all you need to do. I have a lot of work to do. I cannot do it within my single, Python process. I need to schedule these tasks and have someone else pick them up. That's it. You could literally say the interface is, I'm going to write a text file into my local file system that is mounted somewhere else, and some other process, some other job reads those text files and begins taking these tasks. That's pretty much all you need. So there's literally nothing fancy at this level. At the advanced level, I would begin adding stuff like task dependencies, task priorities, and scheduling parameters. Dependencies are tricky because we'll get to this in a bit, but the idea is that if all the tasks are independent, your system is perfectly shardable. It's horizontally scalable infinitely because every single task is independent. You can just say, I'm going to take the task ID hash modulo 100, and your system scales 100x. That's as trivial as it gets. Once you have dependencies, things are tricky, especially once you consider corner cases such as, I have one task that has to be run after another 1,000 tasks have completed. So in a lot of standard solutions where you use a database, for example, do you look at the counter or the list of incomplete tasks every single time this task can potentially run? So you have 1K dependencies. The first of them is completed. The first of them is done. Do you run a SQL query thinking, oh, are there any left? Oh my God, I have 999 left, too early. Then the next one it completes. How many do I have left? 998. It works, but it's really a bit too ineffective. So once you start thinking about task dependencies, you immediately realize a perfectly scalable system would have extra costs associated with the number of shards. And this cost would run at least quadratically, so not so easy to scale. Task priorities, again, in most cases, you don't really need proper priorities. In most cases, you can just emulate them by using different queues, like higher priority tasks and everything else, for example. But it has to be said that some non-trivial prioritization may be in order. You could say, you know what, sometimes during peak hours, I have some OLAP jobs, analytic jobs, and they need to run, but they can wait for an hour or so. It's far more important to run the current production tasks. So it's surprisingly tricky to implement these priorities in certain designs where you did not think of them beforehand. That's why I think for a good advanced level problem statement, you need to at least begin thinking about priorities. Finally, in the basic case, all the task executors, all the workers are identical, more or less. You can just assume they are identical. Maybe they can take 2, 3, 5 tasks in parallel. The single virtual machine can pretend to be 10 workers. Details. The point is, they're all fungible. They're all replaceable. In practice, it's hardly the case. For many tasks, you don't care. Some tasks need a GPU, for example, if it's a machine learning model training. You may have a fleet of workers where only 10% of them have the GPU available. Or you need multiple cores or enough RAM. So in practice, of course, this would go into your task scheduling metadata parameters, but then the worker that takes the next task should be aware of whether it's capable of taking this next task, or should it pull from a different queue. So that's, again, the term queue here is a bit vague because it depends on your implementation. So we're still at the problem statement phase. At the problem statement level, once you begin having scheduling parameters per task, your design becomes trickier. Report generation would be a good example here. You can have a master like big report once you have all the sub-reports computed, in which case you can write a script. You can schedule this big report manually after the small ones are done. But then your machine that runs this script is a point of failure. If it's your local laptop and suddenly you're offline, things go bad. If you run this on a single machine in a data center, this machine can be decommissioned. So once you already have the task queue that orchestrates tasks, you probably want to have this script that runs B after A, and then C in parallel, and then D after B and C are complete. You want this logic to be done by the task scheduler, by the task queue, not by your own script. I think on the mindset level, when I'm thinking about the difference between basic and advanced, on the advanced level of problem statement, the keyword is decoupling. That's actually quite an important step forward. We don't just schedule tasks. We schedule tasks for the purpose of decoupling tasks origination and tasks execution. That's no longer a hack. It's a design pattern. You want to make sure the piece of code that yields tasks can yield them pretty much at any capacity, and you want to assume that somehow, eventually, down the road, they are executed. Sometime, somewhere else. I don't care. I just emit the tasks to be executed. For the expert tier, that's where the true SysDesign comes into play. Full disclosure, I'm a huge fan of high availability, durability, consensus protocols and stuff. I'm first to admit it's in most cases unnecessary to go this deeply, but for the sake of this conversation, I think we should. So for the true world scale distributed task queue, when I say distributed, I mean the user shouldn't care how many nodes it runs on. It should just be available, period. In practice, what it would almost always result in, let me take a small step back. For the super basic use case, you can say I have one server that runs the task queue, and I assume it's never dead. If it's dead, I have to recover some tasks manually. It can take a while, hours of downtime, maybe lost tasks, or maybe lost task results, double processing. Super rare, I don't care, I can live with that. For the advanced use case, traditionally I would imagine the person who formulates the problem in the advanced way on the previous slide, they would say, one machine is a single point of failure. Let's have at least two. So they would have the runner, the leader, and a hot backup. If the leader dies, you have a semi-automatic process where the hot backup takes over. That's perfectly fine, and that certainly effectively doubles your number of nines. So if you had 4 nines, 99.99 uptime in the first design with one machine, mathematically speaking, it's not true in practice, but mathematically speaking, 4 nines become 8 nines. So 2 machines are a lot better than 1 machine, especially if they are in different countries, different data centers, or whatnot. For expert level, 2 is not enough. For expert level, traditionally, since it's about consensus, you would take an odd number of machines, 3, 5, 7, so that if as long as half of them rounded up are still operational and can talk to each other, the system runs as if nothing happens. So the smallest number here would be 3. I can have 3 machines, and then if any one of them dies, to the end user, nothing happened. The task queue still works. As I said in the beginning, even 1 machine should be good enough in terms of CPU load to run all these tasks at dozens per second. That's so small, it's peanuts. So it's really the case that the user should not notice, even if of 5 machines, 2 have died. It should just work. In practice, of these 5 machines, there would be 1 leader and 2 backups, and we're good to go. The tricky part is, what if more than half of the machine die? So you have 5 machines and 3 have died. In my book, for an extra problem statement, nothing should break. In fact, the tasks that are already scheduled should still run, and maybe the tasks that are pre-scheduled, more or less, if they were somehow assigned to certain machines that are still not dead, they can still be claimed by the workers. I would not require that, but it's a nice-to-have feature. What I think is perfectly fine, and what I would expect from such a system, is that it stops accepting new tasks if more than half of the nodes are dead, because they can't. We will have the split brain scenario. If you have 2 machines running out of 5, and then 3 others wake up, what if you are only talking to 2 machines and the 3 are still running in a different part of the world because your continent is offline? Since you want a consistent picture of the fleet, you cannot just afford to schedule new tasks if you can only see 2 machines out of 5. Then in the expert mode, I would say I really want my tasks to be reproducible. A good example would be if my tasks are computing something important, you can actually make it such that on the task queue level, you could say that in the task scheduling configuration, in the parameters, run this task at least 3 times on 3 different machines, in at least 2 different geolocations to be safe, maybe on 2 different architectures. Run it once on AMD 64 and once on ARM, and only declare it successful if the results match. That's a reasonable assumption for important tasks. And of course, this requires not using random number generators because they would not be consistent if you run the task twice and it uses randomness. So if they do use randomness or clocks, this has to be carefully mocked. And then if it's pseudo-random, then pseudo-random seeds should also be stored as part of this audit logs. So if you have to debug it, you know how to reproduce the run locally and see what exactly went wrong. And the last part of this extra program statement would be the dreaded exactly once guarantee. So I can talk about this for hours, but basically exactly once is almost impossible in theory. In practice, you can get to exactly once as long as you own the whole stack from A to B. So it's really hard to guarantee exactly once processing. So in practice, it's always replaced by exactly once side effects generation. So for example, if there's a process at the end of which an email is sent to the user, exactly once from the user's perspective means they receive 1 email, not 0 and not 2. So clearly, for those of you who don't know me well, I talk about this a lot. Clearly, it's impossible in practice because you can send an email to the email server. The email server can receive the email, send email request, and then it could die, or the router could die before the confirmation is sent back to your machine that talks to the email server. So there's a moment in this handoff. It could be quite small, but there is a moment where if the system dies, you cannot even tell if the action has been completed or no. So for true exactly once to happen, you need to have email protocol that guarantees that I'm going to send an email with this body and this email ID. If I try to send it again, don't send this email again because with the same ID, the action has already completed. That's called idempotency. These will be idempotency tokens. We'll talk about them soon. But the idea is you cannot get to exactly once for real, but you can get damn close. And with respect to the stuff you totally own, a good example here would be cryptocurrencies. If it's a blockchain, if it's a ledger, if it's fully owned by you, you can actually ensure exactly once. It could be expensive, could be cryptographically tricky, but it's possible. So with external systems, exactly once, nearly possible. With your own system, entirely possible. What I just talked about is called idempotency on the task creation level, and fencing tokens on the side effect generation part. I have a slide about this. We'll get to it shortly. An example here would be when you run payroll. If you're a huge company and you have an accounting department, and in the US it's twice per month, so every 1st and every 15th and every 31st day of the month, people get paid. So there's an action that you would say run payroll. You pretty much click, tick, select every single user to be paid. And then the huge system behind the scenes on this payroll provider side would compute all the taxes, would make all the payments, would debit your bank, would credit the banks of all the people who need to be paid, would report it to the tax authorities. So that's an example of a bunch of jobs that have some inner dependencies on one another that should happen or not happen exactly once. It would be terrible if people are not paid. It's about as terrible if they're paid twice. So that's ideally, I want my task queues to be durable enough for me to trust them with this kind of task. And the mindset change here is that for the exactly once friendly task queue, I would go as far as saying that the task queue itself is a source of truth for whatever has to happen. I would trust the task queue more than I would trust my database. So imagine I have the Postgres database that run a single node Postgres, because Postgres is generally a single node. Imagine I have this Postgres and I keep data on my payroll runs there. My task queue should be, by definition, orders of magnitude more reliable than this Postgres. If something goes wrong and my Postgres is dead in the middle of me running the payroll, I would actually call the payroll company and ask their admins. I would pray their admins to send me their logs for me to recover from the state in my own database so that I know if the payroll was run or was not run. That's the spirit. That's the degree to which I would like it to be reliable. The next question oftentimes is about the API. That's healthy, that's normal. Let's talk about the API. But I think before we talk about the API in this task queue problem, it's important to agree that there are at least two APIs. There's the API facing the end user and the API by means of which the queue and the workers communicate. And again, this is going to be a personal preference. I'm not particularly biased in either direction, but in my book, the task queue itself does not own the workers. If you're asked to design a task queue, the workers are a special entity. They're a special beast. So in my book, it should be important for my design to support agent workers. Ideally, I could add them dynamically. I could add different kinds of workers, have a machine in my kitchen that is online. I just run a script. It can be the worker, spin up AWS machines, turn on Hessler machines, run some quantum computers, use my cell phone or old tablet. I don't care. They all can be workers as long as they can run the tasks. So to me, the task queue problem is about orchestrating tasks and delivering them to the workers. How do the workers run these tasks is secondary. It's important to have the end-to-end picture in our heads. But when I talk about the queue itself, I deliberately leave the workers out of scope. With this being said, there will be two APIs. There's a bottom line here that is important. When I separate workers from the queue, what I mean is that when the queue development is complete, when the queue is shipped, when the team that has built the queue declares its job done, the maintenance of this queue in production is no longer engineering work. It's DevOps. So it's a different conversation, but it's a bit like when you write your code, you can have your own endpoints configured in your own code, but when it's run in production, it's probably run under Nginx or Apache. So it's no longer the engineer. It's the admin, the SRE, the DevOps that is handling all those routing rules. Just because they can change dynamically, and you would not want to change the code for that. Same goes with the task queue. Ideally, the task queue does the orchestration, the execution, and the worker logic is handled by someone else who is not an engineer. So with this being said, the user API to create tasks is kind of straightforward. That's probably the easiest slide ever in my slide decks in this meetup. So what the user wants to do is, I want to create tasks. Maybe I want to set their parameters. Most likely upon creation. That's it. I want to know if the task has completed or failed, or if it's still running. If it's running for longer than I expected, I would like to see the logs. There's a delicate question about push versus pull. Maybe I don't want to poll every single task status. I want to be notified externally from the queue. Hey, you sent 10 tasks. These 2 are done now. That's part of the API contract, but it's still details. You may want to delete tasks. It's an open question if you can delete the task that is currently running. That's actually tricky. I mean, you could physically kill it. You could send a network packet. You could send a command to the worker. Hey, this task is no longer needed. You can't really guarantee how quickly this deletion happens. That's the gray area. But I think as part of the API, it's fair to say I should be able to delete tasks. The only tricky questions here are this push versus pull. Do I have to poll the service for every single task I created, or am I notified once they succeed or fail? And this task creation part. The task creation is the light version of exactly once. It's the light version of not doing the same work twice. My favorite example is, so it's all about idempotency. Idempotency is the idea that once there is a physical process that results in the request happening, ideally, let's say it's the user, let's say it's a human being, want to transfer money. At some point, maybe I would click a button, pay now. Or maybe if it's a bank, they would ask me for a 2-factor code. Ideally, if something goes wrong, if the backend server that received this request has died, or the network became slow, if I was sending money while my plane was taking off, so my internet was flaky, it's okay if it's not sent, or it's not okay if it's sent twice. It often happens with Facebook. I leave a comment when the plane is taking off, And then when I land, I realized it was posted 4 times because Facebook is too lazy to use idempotency correctly. So in practice, what you would do is on the very client side that originates the request from the end user, it would generate some random string, UUID or whatnot. Could be an integer. You would augment your request with this token, and then the server would deduplicate these requests. So the server could say, oh, I'm seeing the request, but it's the same request with the same idempotency token. I'm going to ignore it. That's pretty much it. The only trick here is that once you have idempotency for real, you can no longer shard horizontally. Because even if all the tasks are independent, this database of idempotency tokens has to be shared across all the shards. So it becomes your point of failure, more or less. There are techniques to work around this. You can shard the database of idempotency tokens by the hash of the idempotency token itself. It's something I would talk about if that's an interview, but in practice, as long as we understand this, we're good to go. Point being here is that the user API to create tasks is really nothing fancy. As I said in the beginning, you can literally create a file on a remote file system and assume somebody takes this file as their job request. I know for a fact systems like this exist. That's nothing extraordinary. For the workers, before we talk about the API, I think it's essential to figure out how hardwired, how hard-coded do we want to deal with our workers. So the design where just say my system has 10 workers with fixed IP addresses on my local network. It's feasible. You can live with it. I think it's suboptimal. You can improve it quite a bit. Ideally, you want to be able to add workers dynamically. Well, not you, the admins, the SREs, the DevOps. In fact, I would go as far as saying I could have several clusters of workers. I could have 10 machines in my on-prem data center. I could have another 50 machines in some cloud. I could have another 10 machines in a cloud in a different country, or maybe in a data center in a different country. In fact, my task setup might require me to schedule some tasks in that remote data center for latency, for legal, for price reasons. You could have some workers hidden behind some virtual private cluster of certain bank or so, where you're not allowed to take their data away. So ideally, all of this is taken care of by the task queue. So my point here is, it's not hard to design the task queue so that the workers are pluggable. You can just add them and remove them as you please, and the system will just work. The second bit of API design about workers is what is in the payload that is the task that is scheduled. Most people would say, hey, it's a JSON or an XML or a binary globe, which can be arbitrarily large. But it's not really a good idea if your task creation request is in megabytes or gigabytes. In practice, if you need to access some resource, my first example earlier today was about video processing. So if the job is to process some video, to post-process some video, I would imagine that the video is stored somewhere in a file system that is available to this service. So it's pointless to put the whole video content into this task queue. You would put an ID, like a distributed file system, full path name. You can go as far as saying that every single bit of data about the task should be stored in this file system. So the task queue could only contain task IDs. They could literally be in 64s. You could have this dedicated directory in your distributed file system with task metadata. That's a bit too extreme. If you want super high performance, I would actually recommend that. But we're not talking super high performance here. So my instinct is JSONs are fine, XMLs are fine. Just keep them small-ish, like tens of kilobytes max. In fact, this file system would really help you because it's hardly just about running tasks. You want to have some debug logs. What if it was rescheduled? How long did it take between tasks submitted, task assigned to a worker, task accepted by the worker started the task, worker task done. You want this paper trail, you want this audit log, and the best place to put it would be into this distributed file system. Actually, Amazon does it this way. If you want to run stuff on Amazon, if you want some debug logs, they would just say, fine, give me an S3 bucket, and I'll put log files there. That's healthy, that's normal. That's how things should be done. The worker API. So the biggest question here is, at least one of the biggest questions here is, do the workers pull the tasks from the task queue, or does the task queue push the tasks to the worker? And I think the answer depends entirely on how many tasks do you have and how big, how frequent are they. If it's this on-demand video processing, so it's literally single-digit tasks per second worldwide in the whole system. I think it's okay if a single task takes minutes, if not hours. If it's okay that the worker asks for the task, receives the task ID, the task queue marks this task as handed off to this worker. The worker works on it. Eventually, the worker tells the task queue, "Hey, I'm done." The response code is X. You can notify the creator of the task. The file with the results is there. And by the way, I can take a new task. Send me the ID, please. That's normal. If it's not single digit per second, but if it's more like millions, then you don't really want workers to ask the task queue nodes, "Hey, do you have new tasks for me?" Oh no, then you ask in the next millisecond, "Do you have new tasks for me?" So the rest depends on your preference. The standard solution here would be to have a proper push notification interface, like Rabbit, Kafka, WebSocket, TCP socket, or whatnot. I don't think it's that important. It can be long polling. It's not a bottleneck here. The point is the interface, the API design. The closer you are to high performance, the more you should be push first, and the more you should be reluctant to use pull or polling. The related question here is, if there's plenty of tasks, polling them one by one could be tricky, because even if it's push, even if you have a socket open to your worker, even if a task is sent to this worker, if it's just one task or 100 tasks, if it's 100 independent tasks, you need to confirm the receipt of each of them. Maybe you don't want to confirm more than, 8, because you only have 8 cores. So at some point, you would need some batch in there. On the socket level, it doesn't matter. You will still do it one by one. On the API contract level, the task queue itself may want to assign tasks in batches to reduce the load on its highly concurrent part. So maybe if you literally process 10K tasks per second and you have 100 workers, chances are you want to pre-allocate the work for the next few seconds for certain worker ID, because in the vast majority of cases, the worker would not be dead. So you have this pre-spliced queues for each worker, and they just know what to do. If the worker dies, it's the job of the task queue to take the part of this worker's queue that is not processed yet and distribute it across other workers' queues. But that's, if you're at this level of throughput, of performance, you may need to get creative. But again, for small tasks, for infrequent tasks, one by one is just fine. And the tricky part here is keep alive and worker failures. Most of us would immediately say, well, most people would immediately say, well, if the worker is not responding for, let's say, 10 seconds straight, and I ping the worker every second or so, I'm going to assume it's dead. That's level 1 thinking. Above level 0, below level 2. Level 2 thinking would be that if I cannot get a keep alive from the worker, well, it proves nothing. It can just, my network link could be dead. The worker could be overloaded with kernel queues, Java garbage collection kicked in. It's actually working hard on my task. I just don't know that. And then you get all sorts of distributed consensus problems where you mentally declare the worker dead, and then the second after you've rescheduled this task to another worker, this worker comes back and says, "Hey, I'm done. Your task is ready." And then what do you do? If the task had side effects like send an email or transfer money, you're screwed. So that's an expert mode question. We won't go there on this slide, but the point is keep alive and keep in track of the health of each individual worker. That's quite some domain of problems, and that's absolutely part of the API between your task queue and the worker. But fundamentally, this API is also nothing difficult, nothing incomprehensible. Somehow the tasks get delivered to the worker, push or pull. The worker can report back with task status, error or success, and the worker has to be kept alive, as in it should send its heartbeats, keep alive messages, or respond to them, so that the task queue knows the worker is still in business. That's it. Let's begin designing this for real. So again, it's a bit of my interview background showing. But I think task queue is quite a standard problem. And standard problems are usually asked with some standard solution in mind. Solution could be an overkill. The point is, there are some important pieces to focus on. There is some priority to work on. If I ask somebody about a task queue and they begin talking to me about how cron works, chances are they miss the point. If you start talking about priority queues, we miss the point. So to me, it's subjective. I'm not claiming it to be the source of truth. But to me, the biggest and the most interesting and challenging part of the task queue problem is how to keep the workers busy. So I think it's actually a failed design. If you have 10 workers, you have 100 tasks, you somehow pre-assign tasks to workers, and then you end up in a situation where 9 workers are idle, and the 10th worker has some backlog. It just shouldn't happen. That's exactly what your task queue should prevent. That's pretty much the thing you use a task queue for. And in practice, workers are often more expensive to run than the task queue nodes. And honestly, as we just discussed before, the task queue itself, if you take the workers out, the task queue itself will be just a few machines. And they're not the beefiest machines. The workers are the expensive ones. So if your task queue, if it's multiple machines, they most likely are not using all the CPUs. So you can squeeze more complex logic there, and you should, because your primary goal should not be to optimize the task queue nodes. Your primary goal should be to load the workers correctly. So I always like designing systems thinking of what can you do if you have an indestructible always online machine. It's a good thought experiment. It's a good first approximation. What if you have a machine that is super powerful? It can run everything. How far does it go? And when does it start failing? And what's the failure mode? So for the task queue, the answer is, I think, super trivial. A single box can do everything. If it's just 1 billion tasks per day, that's just 1,200, 1,200 per second, I think, which is nothing. I can handle millions per second. In terms of data structures for priority queues and TCP sockets, that's trivial. That's far within the limits of a single box. I'm only saying this to illustrate that for the distributed task queue problem, the CPU of the single box would not be an issue. The issue is to orchestrate it across different machines. What if this box dies? You probably have a backup. How do you make sure that once this box that is now dead, once this box is dead, the other one takes over from the right place? Again, no double processing, no lost tasks. How do you make sure that if you have a consensus across a cluster of nodes, how do you make sure the reelection happens quickly? How do you keep the tasks persistent durably? Maybe at the time you create a task, you only return to the user once at least 3 machines of 5 have at least accepted this task request and persisted it in memory or on disk. That's the interesting part to me. And yeah, we're going to focus on this for the true design. I'm fully aware that it's the advanced, if not the expert mode of solving this problem. I just feel it's my duty to talk about this in depth, because once you understand this, the rest is kind of trivial. The other extreme of designing such a system is, so the first extreme was, if I have a beefy machine that is never offline and super powerful, can I do everything on it? Yes, you can. The other extreme is, can I be shared nothing? The now popular hipsterish way of saying, hey, I'm gonna build my system in a way that scales in the cloud. Machines are fungible. If they die, some other machines come into play. I just want to build a system that can live under these circumstances. And the now common term is shared nothing. Shared nothing means the nodes just don't really talk to each other. They use some standard primitives behind the scenes, ideally cloud primitives, so you can outsource keeping their reliability to a third party. So let's say you have a distributed database that you can trust. You have some message brokers that run in the cloud. You pay Google, Amazon, Microsoft, Oracle, whatnot, to run those brokers and queues. So you trust them. For distributed consensus, there also are solutions. And the last thing you want to do, trust me, is to implement your own. So you just say, hey, I have this external third-party cloud-based consensus protocol that works for me. So seemingly, it's not hard to just leverage these primitives and build a distributed task queue. What can possibly go wrong? In fact, I would go further, and I would say that in the modern world, a lot of databases and/or message buses and brokers, they already have distributed consensus techniques within them. Kafka used to run on Zookeeper. Kafka now has its own built-in RAF-based protocol. Every single multi-leader database that currently has consistency absolutely has some distributed protocol consensus in place. So as long as the database claims that you can run it on 5 machines and any 2 of them die, it will not affect the user, there is something super non-trivial behind the scenes. And if you trust this database, which you most likely do, why don't you trust it with your tasks to be scheduled? That's a plausible question, and that's a very legit question. And I want to be upfront. You can't build the system this way. It's going to work. There's nothing scary with that. What could not work is, before I answer this question, I'm going to answer it for the expert mode. So the tightest constraints possible, as I outlined before. I want super high durability. I want to never lose tasks. I want high availability so that the API to schedule new tasks is always available, even if almost half of my nodes are dead. If my task queue is run on 7 machines, if any 4 are accessible by me and among each other, I should be able to operate the system. I want strictly exactly once with idempotency on the task creation side. That's easy. And with fencing tokens on the task execution side effects. That's hard. I'll talk about this soon. And I want the system to not fail me with all these tricky distributed failure scenarios. So as I said before, we're trying to, the worker is failing a health check, you think it's dead, you reschedule the task, and then the worker comes back at you and says, hey, I'm done. This task is completed. What's next? So if you don't need all these requirements, I want to make it very clear that you absolutely can use this shared nothing paradigm and build a good, reliable system. It's going to work. And in most practical real-life cases, in fact, the cost of living with those imperfections would be quite low. So it's infeasible to build a proper system. My view is that it's important for us, the architects, system designers. It's important for us to reason about this correctly, but we don't need to over-design for the sake of over-designing. It's not important to solve the problem that is not postulated. So as I said before, for the web crawler task, if I recrawl every 1000th page for the second time, the world is not going to stop. No one really cares. If it's a financial transactions ledger, things get difficult, but that's a different conversation altogether. So even though I'm going to criticize shared nothing architecture as the foundation for the distributed task queue, I want to be very clear that it is absolutely possible in the real life, and it's actually a recommended solution for many real life use cases. Why could shared nothing not work? I've meditated on this for a bit. I've came up with a bunch of reasons, and I've grouped them together into these 3 sections based specifically on these 3 levels of problem understanding. So for the basic reasons, why might it not work? So let me clarify this. I've grouped the reasons for why shared nothing might not work into 3 levels of problem statement understanding, but I'm still solving the problem at the expert level. I'm still expecting the solution to be highly available, durable, exactly once, and all this stuff. It's the reasoning, the level of explanations for why it may not work that differs in these 3 levels. The problem is still the expert mode one. So the trivial reasons, the basic reasons it might not work, I think, is that at some point your tasks begin depending on one another. If they're all independent, we started from that. If they're all independent, you have infinite scalability by design. Take the task ID or task idempotency token hash modular a big number, have this big number of clusters of machines or whatnot. It works. You can just live with it. What it would not do is if you begin having task dependencies. If task B has to start after task A, task B doesn't even know can it start right now when it's scheduled. after task A is done is it has no idea where to go for to notify task B. If you have task Z that starts after 100 tasks A1, A2 to A100, you need to keep track of how many are left. That's hard too. Where do you keep track of this? In some database? Where does this database live? What if it's dead? If it's sharded, what if it's inconsistent? How do you make sure you get to zero exactly once? To zero unmet dependencies. So that's the tricky mode, which shared nothing doesn't really take care of. If you want to be shared nothing in practice, you can build your task queue workers, task queue schedulers, shared nothing. As long as you have a reliable, consistent database running on your shared nothing architecture. So you could say, hey, I'm going to build my own system as a shared nothing thingy, but I'm going to install Kafka on my machines, and I'm going to rely on its own internal consistency protocols, guarantees, quorum, consensus, so that this part gives me the consistency. That's okay. That's possible. I just feel like it's important to talk about this. As long as we can explain this in simple terms, we're good. I've met people to whom it's hard to explain why shared nothing does not work, and I feel it's important to keep talking about this. For advanced level reasons, I think everything I've put here falls under the category of distributed consensus source of truth problems. So if a task has to be rescheduled between different workers because the original worker died, so the idea that the task has some state, as in not yet scheduled, or being run by worker X, or in process of being taken away from worker X to worker Y. As long as you want this to be handled correctly, you need the task state to be observed consistently by all the components. Or if it's not observed consistently, you want all the components to have the logic that is fully aware that what they see might not be inconsistent. And that's exactly where shared nothing fails. That's exactly why I don't like Mongo for these reasons, because you just cannot guarantee that reading from other shards gives you consistent results. And if you truly want to be exactly once execution, if you truly want to execute your code exactly once, to run your tasks exactly once on a shared nothing architecture, you would reinvent everything from scratch, and it would be easier to reinvent it from a more solid foundation that is not trying to use the shared nothing primitive shared nothing logic. That's probably vague enough, but that's the best I could phrase it as of now, at an advanced level. At the expert level, in a way, at least for me, things get easier, because at the expert level, I expect people I speak with to understand the concepts of the expert level. And the biggest concept here would be atomicity of operations, when the data has to cross the boundary between different universes. So if your source of truth is in Postgres, hypothetically making this up, and at some point it has to go into Kafka. On the one hand, both pieces can be optimized to be durable. You can have a Postgres cluster that is presumably multi-literal action, so you can trust the data to be durable here. That's not hard. I mean, it's hard, but it's not impossible. There are standard solutions. You can say, within my Kafka, I'm going to have multiple partitions, multiple replicas of each partition, of each topic. I'm in good shape. This is reliable. But every single time you want an atomic operation that takes the data that was the source of truth of which was within your Postgres, and you want this data to atomically migrate into Kafka, this operation is nearly impossible to be run atomically unless you have a lot of checks and balances. In practice, you would need to reinvent two-phase commits, or build what is called sagas, or use some other patterns like a transactional outbox, which are all not hard to comprehend. But once you start thinking in these terms, you would realize that you're not using most of the guarantees of this seemingly consistent systems on each side of the fence. So once is critical for you, you cannot afford to assume your components, however strongly consistent they are. You cannot afford they can talk to each other in a consistent fashion. And once the complexity is not within each component, but with orchestrating them, your true complexity of the problem is 100% within the orchestrator. And if it's your own orchestrator, all these advanced techniques that you have on both sides of the fence are similarly necessary. You can literally use text files or simple random key value stores with eventual consistency like Cassandra or Dynamo. You can build proper task scheduler that respects all these guarantees within Dynamo or Cassandra, as long as the orchestrator does the job well. And if you already have to build this orchestrator correctly, Kafka or other similarly consistently guaranteed system doesn't buy you much. I hope it was moderately understandable. I don't think I've done a great job phrasing this, but that's what I can do at this hour. Now I'm going to focus on a couple techniques, a couple technologies that may or rather should not be used for this particular problem. First on the list is Mongo. I think Mongo is an awesome technology. I think people who build it are great. They know exactly what the world needs. I have total respect for them. I just don't think Mongo applies anywhere where you have to worry about consistency. That's just I could be wrong, I might be off. It's just a personal opinion. Because like every other release cycle, every other few months, I'm reading about crazy issues with Mongo losing data. Even if data loss is not an issue, I do hope it's not. When you have multiple nodes, none of which has a data authority over a bit of data, and you're trying to do consistent reads, you have a new shard of your system that connects to a different shard of node, and it's just impossible to guarantee that you would receive the same data from the same place. Your node restarts, it connects to a different Mongo node, and suddenly you get stale data. You get stale data. You get the data that was correct before, but not right now. And your code has to correct for that on your own business logic. Painful, tricky, don't do it. Once again, obligatory disclaimer, as long as all this applies if you need strong consistency exactly once, fencing tokens and stuff. By the way, fencing tokens within Mongo is also a terrible idea. The biggest value that fencing tokens give you is that once you revoke an old token, it is no longer possible to use. So if you have a 0.001% chance the fencing token will be reused, because the part where you validated with, the part where you read this from, the current fencing token from, if it's still behind, if it's not correct, it's too late. You failed. I mean, in theory, that's true. In practice, you can still live with mild imperfections, but we're trying to be in expert mode here, so nope, doesn't work. Rabbit. Well, I have a lot more respect to Rabbit than to Mongo. I just don't think Rabbit is designed for persistence. I know certain teams or even companies rely on Rabbit for long-term, mid-term persistence. I know you can always buy persistence within Rabbit by adding more machines and by configuring certain parameters. I just don't think in the source of truth world, Rabbit is good enough in terms of keeping track of the correct current state of the data. With this being said, unlike Kafka, Rabbit is a smart broker done consumer. So the MQP protocol is really about Rabbit being a smart broker. And when it comes to the component that actually figures out how to assign individual tasks to individual workers, AMQP could be awesome. So in the lower half of the slide, I have this concept that you could actually leverage Rabbit quite a bit, as long as what writes to Rabbit is not the end user scheduling tasks, but your own middle layer. And what reads from Rabbit is also not your ultimate workers, but your own middleware that ultimately delivers these tasks through Rabbit to the final workers. So as long as you can have this three-stage process, the middle of the three stages can well be Rabbit. It would be a good idea. It could do priorities. It could do invariant check-in. It could make sure that if your task needs a GPU, it can only go to a machine with a GPU. It can even do some sort of exactly once guarantees. That's okay. That's fine to use Rabbit for this part. It's just when people tell me I'm going to use Rabbit as the task queue, I'm terrified because chances are there's quite a few huge white areas which this person doesn't really think about. So these were two negative-ish disclaimers. Again, I'm not saying you should not do it. I'm just saying there are cans of worms questions to be at least aware of. Now towards good examples. Kafka would actually be a good technique to use for the task queue. Kafka is the opposite of Rabbit. It's a dumb broker, smart consumer. So on the consumer side, if your tasks are within a Kafka stream, on the consumer side, you would receive tasks one by one in a FIFO way, first in, first out, and then it's totally on you what to do with them. So if your tasks are okay to be processed sequentially, if you handle them one by one, you're in good shape. That's exactly what Kafka is good for. Kafka can be configured for high durability. Kafka can actually require partitions to be stored in different machines, so it would not lose data if you have enough partition replication factor. But Kafka can have the same partition of the same topic replicated to multiple places, so durability-wise, Kafka is good. Kafka is as close as you can get to the database if you want it to be a source of truth. And if Kafka is your source of truth, you don't have this cross-fence, cross-border, cross-universe data transfer. So if you need to move the data from Postgres to Kafka, that's tricky. You need to have this two-phase commit magic. But if you say, hey, you know what, Kafka is my source of truth, and my databases are just the views of this Kafka stream, materialized views, that design is solid. You can totally build a system like this. The trick is Kafka is first in, first out, and Kafka is a dumb broker. So you have to be really creative with how you distribute tasks between topics. And you can't really delete tasks from topics. So imagine you have 10 workers and you have 10 topics of one partition each, and you just load them evenly, which sounds like a good first approximation, until you realize that your 9 workers are idle and one is busy with 10 tasks. Clearly, your orchestrator, your task queue may and should want to reorder, rearrange, reassign some tasks to other workers. Well, you can't remove stuff from the Kafka stream. So that's not a problem, you say. I'm going to have a special database that stores the current last assignment of task given the task ID, and I'm going to store the version of this assignment in the database too. And my Kafka contents would be task 42 is to be scheduled, has been put into Kafka topic number 5, so worker number 5 will execute this task once it gets to it. And this very record, task 42 to worker number 5, has the version ID of this assignment scheduling of 1. So if suddenly worker number 5 is too busy and you reassign this task, in your database you bump the version to 2, and it's now assigned to worker number 7. So once worker number 5 eventually and inevitably gets this message, it should check with the database and see that the current version is 2, and I'm only seeing 1, so I should discard this particular task request. Which again is the problem of cross-fence, cross-universe, cross-domain communication. Tons of techniques to work around this. You can have this database run on 10 machines, and you can say I'm going to write to 7 of them and read from at least 4 until I trust this, so I can have some consistency guarantees. Nothing extraordinarily impossible, but it is painful. It's lots of manual work. So if your jobs are unpredictably distributed in the amount of time it would take to run them, if you need to reschedule jobs, Kafka-based task scheduling, I can build a counterexample that would kill it unless you explain really well how exactly would you handle those reassignments. Is it making sense so far?
Can I just ask one question? When you try to cancel tasks in Kafka, maybe you don't have to go outside to store it somewhere else. You can just have basically 2 topics, one for tasks and second for canceling them for every single worker. So it can check if any of his tasks are canceled and skip them. No?
You can. This would work, but then your subscriber, consumer, would need to make sure it reads the cancel request before it should see the cancel request in the second topic before it sees the task scheduling request in the first one. So it's again the dreaded linearizability, total order broadcast problem. How do you? So if you're the scheduler, you push into the second topic where the cancellations are. You push into the cancellation topic. I'm going to cancel this task. You need to get a confirmation that the task is declared cancelled by this worker. So only after you get this confirmation, you can push it to some other worker's execution queue, which is okay. But then the Kafka point is ruined. You need to talk to this service in a point-to-point connection, wait for a confirmation, and then do your job. So it's pointless to have it in a Kafka stream. You might as well have it in a key value store on this particular worker. And then even this is simple. The tricky part is you now have a multi-stage process on your executor, on your task scheduler, on your task queue side. What if you put the cancellation order into this Kafka queue, and then the node of your task queue that has done this first step dies? So the second step, that after you receive this confirmation that the task is canceled, you need to reschedule it on a different node, on a different worker. This second step now has to be done by a different worker of your task queue, by a different node of your task queue. You have leader re-elections. The different node is already available. You have a new leader, but this new leader should know that for this particular confirmation that task 42 was deleted by the queue on worker 5, what it has to do is schedule it on worker 7. It's all doable, but it's just really, really hard. That's a lot of extra work. And if you have to do this work, Kafka doesn't win you much over, let's say, a simple SQL table. And moving on. I was tempted whether I should insert this slide, but I think I should. Despite seemingly contradicting the spirit of the task queue, based on what I just said before, thanks to Maxim's question, in fact, even Postgres would not be a bad choice. It would not lose much to Kafka. Because since we don't need this FIFO, we don't need the order that Kafka guarantees you. For us, it's a liability. The smart consuming part is a liability. Postgres is an ACID RDBMS. It's a relational database. It supports transactions. So it can handle this assignment and reassignment of tasks within its own individual single transaction. So you can rely, or you can trust its guarantees. So it would be a terrible idea to put all the tasks into Postgres and then select from this huge single table every single time a new task has to be scheduled. But you can get creative, and this degree of creativity would not be a lot higher than the degree of creativity if you want to use Kafka. You would have multiple tables, probably would have a single table per worker, so that the transactions there don't really interfere with the transactions that are used to add new tasks. You would migrate data between these tables by some logic in your task queue leader, and these migrations would also be single Postgres transactions. And you can even use auto-increment columns so that your long IDs, like Idempotency tokens, could be collapsed into like almost 1, 2, 3, 4 counters. You could have halts, but you don't care. It's okay. You don't need it to be totally ordered. If you do use Postgres in this degree, you would have all the problems that you have with Kafka plus more. If I were to break such a design, what I would think of right away is, I mean, it's not that I'm being a bad guy. I just think it's important to attack designs and find corner cases. So if you suggest this design, my first instinct is to break it. And the way to break it would be to think of fan-ins and fan-outs. So fan-in, I think, here is when one task is long, and when it succeeds, a huge number of tasks, let's say 1,000 or 1,000,000 tasks, are created. Even if you have one table per worker, you don't need, your dependent tasks would not be created for the same worker. So you would need to lock multiple tables. And this lock in multiple tables most likely will slow down tasks addition from the outside, which is possible, doable, but suboptimal. Ideally, you don't want internal tasks completing to slow down external tasks acceptance. Fan-in is even more fun. If you have 1,000 tasks, and then after all of them are done, one task has to begin executing. Every single time your task is finished, you need to see if it's one of those 1,000 tasks. You need to update this counter, and this update would be cross table, which means you would need to lock the table responsible for the other worker just to decrement the counter by 1. That's also locking a table unnecessarily. Again, in practice, it would be okay because the load is not so high. In practice, you can even optimize it. You can have n² tables, and then so each worker completing tasks would only you have this matrix n by n, where n is number of workers. Each worker that has a task completed looks at its row of this matrix, and then you squash rows into columns by some timer or whenever necessary. So you don't lock the other workers' queues you don't lock worker 7's queues when worker 5 has a task completed, even if you know for a fact this task may be the one that unblocks worker 7. You first decrement the counter on your own shard, and only if that is 0, you go decrement the counter there. Again, nothing fancy, just a lot of trickiness, easy to make a mistake. And of course, Postgres is only presumably cool because it's really awesome as a single node database. Once you have multiple nodes, multi-leader Postgres is not truly here yet. I don't think it's fundamentally possible. So that's why I'm trying to live in the world where we still have decent non-cloud databases, but part of me has considered that cloud wins. I cannot possibly imagine Postgres-based databases to win over, let's say, Spanner. So in the world of enterpriseization, every single good database would eventually be acquired by a cloud provider. So the market for reliable multi-leader RDBMSs is quite small compared to the market of cloud providers per se. So I think chances are all of us, if we have to design such a system, even though Postgres-based solution looks clean and neat and quite powerful in terms of resource utilization, in practice, in our real jobs, all of us would end up talking to our colleagues and architects how to leverage Google or Amazon or Microsoft cloud primitives as opposed to how to leverage Oracle. I hope to be wrong, but that's my instinct so far. A couple slides to wrap this up. I do hope we can squeeze into 1 hour. Idempotency tokens. These are to make sure we don't insert the task twice. So if the same user is trying to create the same task, but somehow the internet is flaky, or has to reconnect to a different backend node, or I was taken off and my wireless is bad. The solution here, I briefly talked about this, let's just recap. On the client side, where the request originates from, it could be a client device, such as my online banking, where I just typed in the 2-factor number so that the transfer can be confirmed. On my client device, or you can trace this request ID from wherever the request actually originated from. So if it's the backend talking to another backend, but this backend is acting on behalf of me, and I was the guy who used my phone to start this transaction, I could take this token, generate it at the origin, and I could take it further with me, and I could say this particular request has to do with this particular token. So if I'm going to send it twice, if I'm going to send this request twice, chances are it's already received. So double check, please, if you have this request in your pipeline. If you do, disregard it. True idempotency as a concept, as a design principle, assumes that the caller would not even notice that the request was serviced before. You send the request. If it's a new request, the server schedules it and sends you back the ID of this request in processing. If the request is already handled by the server or in process of being handled, you just get back the ID of the currently running request. The idea of idempotency, the core idea of idempotency, is that if you make the same request twice, you'll get the same result. So that's how it works. It's not too hard to implement it with the task queue example. I felt obliged to talk about idempotency in more detail because fencing tokens are far more interesting, far more important, and I've seen people have troubles with them, even though fundamentally they're no different than idempotency tokens. So the fencing token is this idea that you want to guarantee exactly once processing. And first thing we do, replace processing by side effects generation. So a good example would be financial transfer, or a clean example would be sending an email. So if at the end of of the task it sends the user an email, the user doesn't really care how many times the task executed. The user cares about receiving the email once and only once. And bear in mind, we are now talking about the dreaded distributed worst-case scenario where you have the node that has claimed this task. It has done some work, maybe prepared the email contents. Then it wants to send the email. It may even have sent the request to send the email to the email server or whatnot. But then this node dies before it can confirm to the task queue that the task has been completed. Or maybe this node never receives the confirmation from the email server, so it cannot possibly know if the email was sent or not. So, as I said before, unless you control the email server, you cannot eliminate this ambiguity for good, but you can shrink it as much as possible. The way to shrink it is what is called fencing tokens. It's as if you require all of your client APIs, such as email providers, email senders, to support idempotency tokens from you. So it's same as idempotency, but in a different direction. It's not what you receive, it's what you send. And then, in order for this to work, there has to be a single source of truth on your side that tells each worker, hey, not only you collect this, you grab this task, please execute it. It tells the worker, execute this task, and here's a fencing token you can use. And every single time this worker has a side effect, in fact, I would recommend in this case that each task has only one side effect. So the task does its job, and then at the end of its execution, if it's successful, all the side effects take place. If there's multiple side effects and multiple steps, make it multiple tasks. That's just a cleaner solution in this case. Otherwise, you have troubles with partially completed tasks, and it's just hard. So if it's so important for you to be exactly once on subtasks level, delegate this subtasking part to the task queue and have multiple tasks. That's very similar, by the way, to how coroutines work and how actor models work from the previous episode. So we're just scaling this idea of async await, but we're scaling this idea to multi-machine deployments. And your executor, your scheduler, is no longer within your CPU, within your kernel space, but it's within the task queue scheduler. So the task queue could die, the task queue leader could be the different one. The executor node could not be your current machine, physical machine, but a totally different computer in a different place of the world. You could do the first step on AMD64, the second step on an ARM. As long as your task is, I begin working, I'm done, here are my side effects, and then the next task is to be scheduled. As long as that's like this, you're in good shape. So back to the topic. Once the task queue hands off the task to the worker, it's not just a task ID. It's a task ID plus the fencing token. The fencing token is stored by the task queue in some durable place so that you can always quickly query, hey, for this task ID, is this the current fencing token? So the task runs on the worker. Eventually it gets to the point where it wants to do its side effects. Every single API it talks to produce side effects, such as the email provider, expects this task to send it not just this email body or whatnot, but this side effect contents plus the fencing token. And this external component is only allowed to perform the operation if the task queue confirms that the fencing token is the same, that the fencing token is still valid. This helps because imagine your worker is not responding for a while. It stops replying to keep alive, so the task queue after some timeout assumes it's dead. It has to reschedule the task to another worker. Before it does so, it invalidates the fencing token. It creates a new one. So at this point, once the fencing token is changed, at this point, if that other task tries to run its side effects, the request to send an email will be rejected because the fencing token was changed. So in fact, your fencing token storage becomes your source of truth on whether the task has completed or not. And you cannot really guarantee task termination immediately, but you can atomically revoke the permissions to create side effects for this particular task running instance by that particular worker. That's how fencing token work. That's how fencing tokens work. I think I explained it well. I don't think I could do it better. It's actually quite a trivial idea. It's, as long as you begin thinking of data ownership in terms of a DAG, of what depends on what, and as long as you you fully contend that some bits of data can be eventually consistent, but some must be strongly consistent. Fencing token must be strongly consistent. If ever your worker or the executor of that email send operation, if it ever can see the stale, the old data on the fencing token, the whole thing doesn't work. You need to guarantee that your email send backend or whichever other backend you talk to, you need to guarantee that this component reads the current state of the fencing token. You need to guarantee that the task queue, when it reassigns the task from worker 7 to worker 11, it needs to guarantee that before it can hand over the task to a different worker, the fencing token is propagated, is changed and propagated to all possible nodes, or whatever your logical means to do it would be. It needs to guarantee that the fencing token is changed so that every consecutive read of the fencing token, read of verification, will be false, would fail for the old token. So that's an example of a strongly consistent piece. That's where consistency is important. That's where the expensive parts of the job is. That's where people who understand this are paid a lot more than those who use Mongo. Yeah, I said it. Okay. We're close to the end. So in conclusion, the task queue is a pretty trivial problem in the basic use case. It has a lot of issues behind the scenes if you want to do it correctly. And honestly, I think it's an awesome problem to talk about because it just shows at which level does the person understand the problem domain. And I would not get tired of saying this. For most real-life applications, you don't need to do all this fanciness. And you can leverage cloud primitives effectively. You can leverage Postgres, Kafka, even Redis. It's going to work. I just felt obliged to cover the advanced use cases because that's who I am. That's what this meetup is for. I hope I did a good job covering the tricky scenarios. I'm fairly certain you can find standard solutions online. My job here is to make sure that you know all the tricky questions that have to be asked once you begin thinking of this problem in depth. I think that's it. Thank you, Fox. And any questions? Now is a good time.
Hey, thank you. It was really awesome. But looks like we haven't discussed the dependency of the tasks problem and how it should be solved, like using the message queue kind of existing kind of Rabbit or Kafka or Postgres. Wasn't it like a target of this talk, or and if it was mentioned several times, but we haven't discussed like any solutions for that?
Yeah, I cheated. I didn't cover this. So with Rabbit, I don't think it's even possible, because with Rabbit, the way Rabbit works behind the scenes is every single message kind of lives in its own envelope, in its own tiny virtual machine. So if you want to use Rabbit for dependency checking, you would need to build, or more like use, some existing Rabbit-based, Erlang-based key value store that is stateful, or more like an actor model that you can send a message to this key value store, hey, are my dependencies met? You would get back the response, yes, they are, or no, they're not. And if they are met, you would actually schedule a task. That works for one-off task scheduling. To schedule the task conditionally on those other tasks completing, you would need to build this whole topology of messages traveling. I don't think you want to use Rabbit for that. I think for that you would actually want to use, so this is, as long as this can be done by less strongly consistent components, you want to do it in a less strongly consistent fashion. So you would build your own component, the job of which is to clean this up. So it's gonna be a node that receives messages about task completion and notifies your other store, be it within Rabbit or no. You would notify that certain tasks are cleared for scheduling. So that's how I would do it. It's kind of simple with Rabbit because this particular service could be shared nothing. It could shard really well as long as you have some periodic cleanup jobs. So if you can have 5 nodes doing that. If one of them dies, you just say, fine, I'm going to go through all the tasks, see what's pending, and carefully check in my database if the dependencies are completed. That's okay. You can do that. With Kafka, I have no idea how to do it correctly, and I suspect it's not possible to do it right, because every single time I think about it with Kafka, when I interview people and they ask me about Kafka, when I interview people and they suggest Kafka as a message as the provider for the task queue, I begin asking them about these tricky cases of tasks rebalancing, because when you have to move task 42 from worker 5 to worker 7, it's not impossible that you would need to move it back to worker 5, because now the task 7 now worker 7 is overloaded. And then for every single algorithm I can think of a counterexample where you would move the tasks too frequently, so that you would a single tricky task, the job to reassign it back and forth would be exponentially higher in CPU and network utilization compared to just running this job. So every single time someone talks to me about using Kafka for these tasks, I'm concerned. So I think with Kafka you can only do it linearly. For dependencies, yeah, I guess again, same thing, right? You would have a separate service. They would keep track of what can be executed right now, and it would this service would be responsible for emitting a signal that some tasks are clear to run. Well, what I need to highlight here is that the service that decides that the task can be run, it does not have to be strongly consistent. It can be eventually consistent. For me, it's important that we respect exactly one's guarantees and we don't lose tasks. If one task out of 100 does not start immediately as all the prerequisites for these tasks are completed, that's not a failure mode. In fact, it might be a desired state if your system is overloaded. So it's clear to me, I don't know how to explain it well, but it's clear to me that this particular component can be eventually consistent. And eventually consistent is infinitely easier to build than strongly consistent. So I only want to focus on the strongly consistent parts.
Yeah, that makes sense. Yes, actually, one more question related to Kafka. So as far as I see, we don't need to preserve the order of the tasks in our task queue. So basically, it looks like the Kafka, it's kind of the one of the main features of the Kafka is the linearizability, and that everything will be processed in the order inside each topic. But we don't actually need to have it. And kind of isn't it given extra overhead on the processing, because we need to have this literal action part or so. So kind of, I don't think that the Kafka is used pretty well here, because of we have some parts which are kind of great to have, but they are optional and they can reduce our throughput or so.
I don't have a clear answer because it's a matter of perception. I agree with the argument 100%. I still think that, so yes, FIFO as the linearizability order becomes a liability for the task queue problem. So seemingly we're using too strong of a tool for something simple. But on the other hand, since Kafka is as close as you can get to a consistent database, which is not a database, using Kafka gets rid of this problem of data authority, source of truth traveling from one universe to another. So in my book, taking care of this source of issues when you need to do two-phase commits, sagas, transactional outboxes and stuff. Since Kafka is one of the standard-ish solutions that eliminates this potential bottleneck, it's worth it. So I'm not a huge fan of Kafka because I think people try to push it everywhere, not as aggressively as Mongo, but still everywhere. So for these reasons, I'm always careful with Kafka. But as an architect, I think once you want consistency between data authorities, if you can afford to have your data authority within Kafka, architecturally it's always a good. It's usually a good design, because you're buying yourself not having to worry about the data ownership crossing the boundary between universes, even though the FIFO part is absolutely redundant here.
Yeah, so it looks like kind of none of the existent options or services really solve the distributed task, kind of this component part for the queue pretty well, because some of them has pros and cons. It looks like some in-house solution, if you have resources, could be much better than using each of those blocks, because some of them has they are not suitable well for each of them. for some part of it.
Yes, exactly. This is exactly the reason why this episode is split into two. Because I wanted to, originally back in January, I think, I wanted to talk about distributed task queue, where the first half of the episode is about Rabbit and Kafka, and then I talk about how to leverage Rabbit or Kafka, how to use them as building blocks for the task queue. And then I quickly realized that it would be too much for one episode, and the topics are not really that intersecting. So on the one hand, the messaging platforms on this planet are far from perfect. So we have some clear leaders like Kafka and Rabbit. You also have cloud primitives. Google pops out. Amazon has SQS, SNS. So on the one hand, you have those primitives. On the other hand, task queue, that is a seemingly trivial problem, does not fit these primitives well. So I wanted to highlight this part. And the question of whether you want to build something from scratch, in-house, versus using something standard, well, that's the core of architecture, right? That's where system design meets business planning, meets budgets, meets what if this genius person writes this code and then leaves a year later and we have to maintain something that's impossible to maintain. I don't think there can be a magic bullet. Like this will always be the question of, and I don't even think this can be logically reasoned about. Every single company I've seen making these decisions, every single time there are a few people who are trusted by the company and they manage each other, and you have to present your arguments to these people. So it's always like we cannot reason about whether these people are right. In my experience, oftentimes, like all the time, these people are reasonable enough so that arguments convince them. And my job here is to show what kinds of arguments work. But whether there is a correct solution, I have no idea. In fact, I doubt it. I think we'll always see a bit of everything, and we should converge to something that is more likely to work than others. But I don't think we're anywhere near this point yet. It's like
For the vast majority of cases, these options will be pretty fine, and if looks like having your in-house solution would take more resources than give an impact or kind of any reason to do that.
My pragmatic advice, ironically or unironically, is to figure out a personal preference on this in-house versus cloud versus on-prem, and work with companies and people that share your vision. That's the path to be happy and to ultimately improve your skills and deliver for the world and for your own satisfaction. Because if there's no alignment on this between you and your manager and your company and the company that pays you, if there's no alignment, you will not convince them, or vice versa. That's my trick that works pretty well so far.
So, can you name some examples of like the use case of this expert mode task queue?
Expert mode. Well, anything financial. Anything that has to do with any smart contract on any blockchain ledger effectively has to be exactly once. Any smart voting, I guess outside this Web3 field, it will be hard, but within Web3, it's super trivial. Let me think for a moment. So in practice, I hear your argument, and I think you're right. In practice, there's one example that Martin Kleppmann likes to use. So imagine you only have one instance of a product in stock, and somehow your system is not bulletproof, and it's possible in theory for two customers to order it. So because you don't have strong consistency, there's one product and two people have paid for it. On the one hand, it's a disaster, and you would want to build your system in a way that this is impossible. On the other hand, what if your factory worker or delivery person breaks it? You certainly, as a business, you certainly have a process by means of which you just apologize to the customer, issue them a refund, give them a gift card, and all good. So in practice, this possible collision of your data integrity process has a cost. And if on the one hand you need to spend another few $1 million to build a better database, and on the other hand you just spent on average $5K a month pleasing customers, clearly the business would pick the latter. So I agree with you that every single improvement towards on this path to expert mode, every single improvement is taking care of another 9 after the decimal point. But the price of this other 9 is exponentially lower. At some point we get to cents and microcents where it's infeasible to think of this.
Yes, but sending money through like Venmo or any other services from one person to another, isn't it like suitable for that?
As someone who lives in America and sees how American banks work, I can assure you they don't care. Like, I could literally transfer money between my banks in circles and have more than I have and use it indefinitely. That's like settlement times can be days and days in different directions, and people abuse it for living sometimes. So it doesn't seem to be an issue that people in America think is important to solve, and I'm pretty sure Venmo as a venture-backed company could not care less.
Okay. Yeah, but kind of maybe for like bank transactions, this stuff. So kind of, I think it should be. I'm not sure whether it's done kind of in this distributed task use or so. I think it's much more bulletproof and like single machine or so, but still kind of it's kind of one of the domains where it could be applicable, like all this banking money stuff.
Without naming names and companies, I can confidently tell you that every single large-scale financial institution has a department whose job is to do reconciliation, and eventually what they do for a living is every week or every quarter they figure out something doesn't add up and they just compensate for it in either direction, and as long as it's fractions of a percent for the company, no one tries to improve these processes. So, I mean, Alexander has a really good point. In practice, it's hard to imagine a use case where all these issues are important. I mean, you can even blame me for being too picky when I interview people and ask about all this stuff. Maybe it's just my fetish to talk about them, but I think it's important to think from first principles and at least see these problems.
And one more dumb question. So kind of you've talked several times about the distributed consensus. So kind of what do you exactly mean? Kind of to which part of the distributed task queue consensus could be like important? Because like kind of it's not clear personally for me, for example, like how it could be applicable for different parts there. Maybe you can elaborate on that. Consensus on what exactly we can need to like to do this in process.
It's the industry standard term. I don't think it has a clear enough definition in a few words. But the best definition I know, that I personally like a lot, but I don't think it's easy to grasp, is that distributed consensus is when a cluster of nodes acts to the external observer as if they are computing the same function. So it's a state machine, and whatever it does, you can write the code by which it operates, by which a state machine operates, and the external observer would not know which of these nodes are up or down, which of them is the leader, if any, are they in the process of swapping. That's a distributed consensus. That's the only solution I know of for the industry, that makes that if you want to make sure that no task is scheduled on 2 machines concurrently, you need a distributed consensus. It's a cat theorem. It's either you have it implemented through leader elections, or you can have a single point of failure. So single machine dies, and until it's manually or semi-manually fixed, no task can be scheduled or rescheduled. Yeah, in practice, go ahead.
Yeah, so basically, like what I hear is that for example, if you have like several machines for scheduling, several nodes, so basically there will be only one leader who will perform all the job, and the rest of them are like just staying there for reliability.
Yes, the trick is, so it's this last bit of confidence. It's almost perfect or perfect. You can have a single leader, and you can have, let's say, five followers, 4 followers to make it even, to make it odd. And then if the leader dies, 4 followers look who has the highest index up to which they are up to date, and this machine becomes a new leader. It's a wonderful design, but how do you guarantee that the index, the offset from which this new leader starts, is the next one after the previous leader. So it's this atomic handoff problem. Maybe the previous leader completed the last operation, the m plus first, but didn't confirm it to the other entities. Or maybe it managed to do a few more, but those other entities are not aware of that because the message did not go through yet. You see, because that's also simply the protocol that makes sure this happens one by one, so that at any time, if this machine fails and the other one takes over, it's guaranteed to go consecutively 1, 2, 3, 4, 5, not 1, 2, 3, 4, 6, or not 1, 2, 3, 4, 4. You can prove it mathematically that as long as you have the piece that assigns indexes from 0 to like I plus 1, incremented by 1, if you have this black box, you're in good shape. So mathematically speaking, distributed consensus is same as total order broadcast. But that would be too academic. In practice, if you can afford small overlaps in either direction, if you allow overlaps, you don't need consensus. If you allow drop in some data, you don't need consensus. If you want exactly ones, there's no other way except the consensus solution. At least not that I'm aware of.
Mm-hmm. Yeah, so it wasn't clear that we'll have only one leader. So if we have leaders, so we need to have leader elections. That's why we need to have distributed consensus. So it makes sense. Yeah.
Well, look. The beauty of system design is that you try your best to not solve hard problems. That's why I keep bringing up Kafka, because Kafka is one of the interest-attended solutions that does leader elections behind the scenes, but you don't need to worry about that. You just know that once you publish something to a stream, it's there with a stamped index, and all the observers would see the same data, the same index. So in my mental model, leader elections and distributed leader elections, such as practice or raft, I don't want to think about this, even though I know how they work. I don't want to think about this because I know they're hard. I want to find the right way to leverage the standard component that handles this part behind the scenes. Logically, I don't need to know if there's a leader, or if they are leaderless somehow. As long as they perform this task of total order broadcast, we're in good shape.
Yes, but kind of still the scheduling part is. Can we rely the scheduling part on some other component? I don't see that.
Well, so what you ultimately want to happen is one task is only assigned to some worker by one node, right? So the failure mode is if task 42 is simultaneously assigned to node 5 and to worker 5 and worker 7 by two different task queue workers.
Okay.
You can say, I'm going to shard it by task ID. I'm going to take a decimal representation, take the last digit, pick a task queue down from 0 to 9. So task 42 ends with 2. So I take the third machine, index 2, 0 based. And this third machine will be responsible for assigning task 42 to a certain worker. That works until this machine number 2 dies. And once the machine number 2 dies, you need to know exactly up to which has it picked up, at which point you're back to this dreaded exactly once problem.
Mm-hmm. Yeah, but kind of still this scheduling part for for example, we have cron job, or we need to even maintain this order kind of between these several tasks. Yes, so kind of we need some component. We should do that. It should be built by our own. We can't rely on some database on some database or on the Kafka because they don't have this functionality out of the box. Yes, and
if you can rely on a database and the assignment of the task to a worker happens atomically within a transaction in this database, like Postgres, you're in good shape because each transaction has either completed or failed. So if your machine that is responsible for assigning task 42, if this machine dies, the next machine that picks up would know exactly from the database in a consistent state, would know exactly if the task 42 has or has not yet been assigned. But this is only possible if you don't need to move stuff between two universes. So if you have Postgres and you use Postgres transactions and all the data lives in Postgres, wonderful. If you need to move data from Postgres to Kafka, that's where issues begin. And Postgres is a wonderful solution as long as you have a magically scalable Postgres with multi-leader multi-leader replication, but I don't think it exists yet. And then you have trade-offs between consistency and availability. So in practice, if you really want this expert mode distributed task queue, Google Spanner might be the best solution for you. That's exactly what you want. And then it becomes a question of cost and availability. Google Spanner is surprise Google. By the way, it's been a couple of years since I started talking about this in my job, in mock interviews, wherever. And I felt it's a big topic back then. Then I had troubles explaining to people why it's big. So the level of questions I get from you guys on this meetup is increasingly awesome. Like I feel like the world starts to catch up with why is this a big topic, why it's an important problem. So thank you so much for asking this. Keep asking further. We can keep going right now. We can talk in Slack or in person. If you help me and help me explain the importance of this concept better, I would greatly appreciate it. All right. Shall we call it? I had a lot of fun. Thank you, and see you next time.